Welcome to the next lecture on algebraic number theory. This lecture is all about discriminants of number fields. So, what can we say? So this kind of builds on the last lecture, where we were talking about computing discriminants. We gave a couple formulas. The point of this lecture is basically to say some useful things about what numbers can appear as the discriminant of a number field. So, overview, and I guess I should be more careful maybe and say the discriminant of a ring of integers in a number field. The discriminant of a number field itself technically is only defined up to like the square of a unit or the square of an element in the field, whereas the discriminant of the ring of integers is a well-defined integer, but it's pretty common abusive notation. So first I want to talk about what the sign of the discriminant has to be. So we can say something about the sign of the discriminant in terms of the arithmetic of the field. Discriminant. I definitely misspelled that. Discriminant. And the second thing I want to talk about is something called Stickelberger's theorem. So this is essentially tells you the value of the discriminant mod 4. Okay. So the first 24.1 proposition. So the first thing is the sign of the discriminant. The sign of the discriminant, let's say of k over q, for a number field k, is -1 to the s, where 2s is the number of non-real embeddings of k into c. 2s is the number of embeddings k into c with image not contained in R. So remember, so I guess just remember there's an even number of these embeddings because they come in complex conjugate pairs. Okay, so how do we prove this? Proof. So we're gonna, since k is a number field, it's got to be some simple extension, and we're gonna let k be q join alpha. And we're going to enumerate the real conjugates of alpha and the complex conjugate pairs of alpha. So enumerate real conjugates of alpha, let's say alpha 1 through alpha r, and the complex conjugates. Yeah, I could see this being confusing in that I'm using conjugate in two words. One is the complex, I'll specify these are the Galois conjugates. Complex Galois conjugates alpha r plus 1, minus 1 bar, so on and so forth, alpha r plus s bar. Okay. Then oh, I see. Yeah, okay. What can I say? The sign of these guys, alpha to the n minus 1, is the sign of... So this discriminant is this guy. So this is using our formula for the discriminant from last time. Alpha r plus I bar. So, however, I've gotten rid of quite a few terms here. What do I want to say? It's the sign of this guy. Okay, what do I want to say here? Sign of this guy. So this is, first of all, this is using 23.2 equation 2, or equation 1, sorry. And the simplification, the primary simplification that I've made here is that the other terms in the above product they're either so they're either in the following form. They're either alpha I minus alpha j squared, the square of a real number, or they're of one of the following forms: alpha r plus I minus alpha j squared, alpha r plus I bar minus alpha j squared, alpha r plus I minus alpha r plus j squared, or alpha r plus I bar minus alpha r plus j squared, or it could also look like this: alpha r plus I minus alpha r plus j bar. Basically the bars could be on the other side here. Alpha r plus I bar minus alpha r plus j bar squared. And these all come in complex conjugate pairs. So we can pair these guys up like this, and these two will product to a positive number, and these two will product to a positive number. And these two will product to a positive number occur in conjugate pairs. Okay. So what do I want to say here? Notice this is going to differ by the square of some rational number from the actual discriminant of our number field. or the actual discriminant. So I guess first of all, maybe I should finish it up like this. Then we have the sign of this guy. Just to compute the sign here, alpha r plus I bar squared. This is the sign. Just computing this interior thing directly gives product I less than or equal to S2I times the imaginary part of alpha r plus I all squared, which comes out to -1 to the s. Okay, so there's something to be a little bit careful of here. This discriminant may not actually be equal to the discriminant of our ring of integers. However, it differs by the square of some rational number. So since t alpha 1 alpha m minus 1 equals disk O sub k over z times a squared for a and q cross. They have the same sign. If you don't like this, you could run a similar argument where instead of just choosing any old arbitrary alpha, choose alpha to be in the ring of integers, which you can always do. And then, and now instead of differing by a square of a rational number, it'll differ by the square of an integer. Okay. So the sign of the discriminant basically corresponds to if you have an even number or an odd number of non-real embeddings. The final thing we have to prove is something called Stickelberger's theorem. So this is 24.2 theorem. This is called Stickelberger's. So we're going to let K be a number field. Then the discriminant is either 0 or 1. Mod 4. Discriminant of O sub k over z is congruent to 0 or 1. Mod 4. Okay. So we're going to choose some basis. Basically, we're going to prove that this discriminant is congruent to a square mod 4. So we're going to choose a basis of OK over Z, and the main tool we're going to use is our formula involving Galois conjugates. Choose a basis of OK over Z. Let's say alpha 1 through alpha m. We're going to let sigma 1 through sigma m be the Q embeddings of K into its Galois closure. I mean, we could just say C. We have, so by our notes on discriminant and Galois theory, the discriminant of O sub k over z. This is the determinant of these sigma sub I of alpha j squared. Okay. So remember, this basically just came down from the formula for trace involving Galois conjugates. And essentially we're going to expand out this determinant using like the actual formula for the determinant. It's kind of messy, but I think it's a good exercise to kind of think about what's going on with this determinant. Recall the determinant has the following expansion over permutations. It's sigma sub I alpha j. This can be written as a sum over permutations in the nth symmetric group of the sign of the permutation tau times the product from I equals 1 to n sigma sub I alpha tau of I. Okay, so we're going to break this sum into two pieces. One for the positive permutations, so P, the sum over even permutations, and N, the sum over odd permutations. Okay, and maybe just to be specific, P is going to be the sum over tau and an of the product I equals 1 to n sigma sub I alpha tau of I, and n is going to be the sum over tau, not an an, product I equals 1 to n sigma sub I alpha tau of I. Okay, so what do we see? We see that the discriminant of O sub k over z, this is p minus n squared, which is p plus n squared minus 4p times n. And the goal, so I claim p plus n and p times n, these are both integers, are integers, and from this we'll see that this discriminant is congruent to a square. Then the discriminant of O sub k over z is a square mod 4, and you can check really quickly that these are only 1 or 0, i.e., well, these are not equivalent, but thus it's congruent to 1 or 4 mod 1 or 0 mod 4. Okay, so it remains to show that p and n are actually integers here. the basic idea is that P and N, so first note P and N, these are definitely going to be algebraic integers. Since, well, they're basically sums and products of Galois conjugates of algebraic. Since Galois conjugates are algebraic integers, Galois conjugates of algebraic integers are algebraic integers. And P and N are products and sums of these. So it really suffices to show, since Z is integrally closed, it suffices to show P plus N and P times N are rational numbers. So it suffices to show P plus N and P times N are rational. Okay, so this is the second take of the proof that P plus N and P times N are rational. I screwed up the first one, but I figured it out, and I'm going to go ahead and edit this in. So we're going to start with omega, an element of the Galois closure of K, or an element of the Galois group of the Galois closure, an element of Galois group of the Galois closure of K. So to show P plus N and P times N are rational, it suffices to show that omega fixes P plus N. So we show omega fixes P plus N and P times N. So in particular, first we show omega of P is either equal to P or N. And for each, okay. So we have omega of, let's say, P, omega sub N, is product over I equals 1 to N sigma sub I alpha tau of I, passing through, since this thing's a field homomorphism, tau and AN product I equals 1 to N omega of sigma sub I alpha tau of I. Okay, now thinking about omega of sigma sub I, this essentially gives me a new embedding of K into the Galois closure, or K into C, however you want to look at it. This gives me a new embedding of K into C, and in fact it acts faithfully and transitively on the collection of embeddings. So I'm going to call this new Galois, or new embedding, sigma sub F of I. So this is another one of my like sigma sub J's, something like this. And then just to have this thing in the right form, this is a tau and AN product sigma sub I alpha tau of F inverse of I. and here f in Fn basically is a permutation with omega of sigma sub I is equal to sigma sub f of I. If f is odd, then this sum is n. So if f is odd and the sum is n, if f is even, then this sum is p. Basically, you can do a similar computation and check the same holds for n. So n is either fixed or permuted to p by this omega. And then basically the result follows. Then omega of p plus n equals p plus n, omega p times n equals p times n. It's not possible that n fixes p and also permutes n to p, because omega has to be a bijection. It's got to be an isomorphism, an automorphism of the Galois closure, and thus p plus n and p times n are rational. Okay, and we already discussed above that they also were integers, and why this finished the proof.